Okay, I'm going to start with a reasonably brief, just reminder of the things that will be on the exam for tomorrow. The exam will be the same format as the last one. I thought I was going to get the last one graded before I left, but I did not. And I had these grandiose ideas of, we get on the airplane at 12:06 a.m. and we get to Lincoln at 9:30 a.m. I could then grade in the morning. Well, my brain was not working for that purpose yesterday, so I did not get additional grading done. So I will certainly have the first exam graded by the time you finish the second exam, but I'm not going to make any promises prior to that. And I know that's a long gap. I'll do better. I'll get the second exam graded before you come back from from Thanksgiving break. Yes, spring break. Michaela's question. Did I have the time wrong? Yeah. I will go back and look at it because, yes, that is not the goal. Thank you for letting me know. Yeah, that would be a real bummer, wouldn't it? Yeah, I'm sorry about that. That would have to be a mistake on my part. Okay, things to know for the exam. First, just a reminder, the exam is over chapters 22 through 24. That is magnetism. And so I left the same figure that we had from chapter 24 because I thought, well, that's a good place to start. So in chapter 22, we learned about magnetism. We learned about natural magnetism and 3 types of natural magnetism. Only one type that we studied carefully, but we needed to know that there are 2 other types. Natural magnetism starts with the actual particles. Electrons have a magnetic moment. They behave as magnets. Protons have a magnetic moment. They behave as magnets. Neutrons have a magnetic moment. They behave as magnets. What do we call the magnetic moment for an electron, a proton, or a neutron?
Spin.
The spin. The spin is the term we have for that because when it was discovered, it was first discovered for electrons, that electrons, when you put them in a magnetic field, they interact like they're little bar magnets. And so they said, well, that could be because, as you've now learned, right, we can now at the end put stuff together to make more sense. If we have charge going in a circle, a solenoid, it creates a strong magnetic field. And so they said the electron's magnetic moment, the fact that it's behaving like a magnet, must mean the electron's spinning around. And it has a charge, so that charge spinning around makes a magnetic moment. It makes perfect sense, except we now know that the electron cannot be spinning fast enough for its size. We don't know the size of the electron, but we know it's smaller than this. And it could not possibly be spinning fast enough to create its magnetic moment. So it has to be an intrinsic thing. That is, electrons simply behave as little bar magnets. It's one of their properties. They have an electric charge. That's a fundamental property. They have a mass charge. That's a fundamental property. And they have a magnetic moment, which means it has a net magnetic charge of 0, but it has a north side and south side. And so the electrons, the protons, and the neutrons, those all have their magnetic moments. They have a spin, and together those are what make the magnetic properties that's natural. And so materials with a natural magnetism are broken up into ferromagnetism, which is strong, like iron, hence the ferro. Strong magnetic behavior is ferromagnetism. Then we had 2 weak magnetic behaviors, paramagnetism and diamagnetism. Paramagnetism is a weak form of ferromagnetism. Diamagnetism is the opposite. Diamagnetism is a magnetism where north attracts north. It's diametrically opposed to normal magnetism where north attracts south and repels north. So the diamagnetism is an odd reverse type of magnetism. And oddly enough, every material has this. But you only notice it if it doesn't have one of the other two, because the diamagnetism is weaker than the others. So the paramagnetism is weak normal magnetism. Diamagnetism is a very weak reverse type of magnetism. Because we have some materials that show a strong magnetic behavior, that magnetic behavior has to do with the nuclei. We will have materials form domains in them, little regions that behave like magnets. And those little domains, on average, would have the domains adding up to 0 for the net magnetic behavior. That's what normally happens in material. So that's why I have iron, like I don't have a stapler here anymore, but well, like this. Here's iron. Here's iron. There's no magnetic interaction at all. Why? Because the magnetic domains are completely randomized, which means the net magnetism in these is 0. But if I bring a magnet to them, that magnet will put a torque on the magnetic domains, aligning them with the magnetic field. And then the magnet will be attracted because it's created an induced magnetism in the magnetic material. If I heat this up to the Curie temperature, those magnetic domains will freely rotate. If I put a magnet here, heat it up, and then freeze it again, those magnetic domains will now be oriented so I made a permanent magnet. So if you have a ferromagnetic material that is just randomly aligned and no magnetism, if you heat it up in the presence of magnetic field, they'll align, you'll create a permanent magnet. Hence the MacGyver episode where MacGyver takes tire iron, whacks it on something, and then uses it to pick up a key. Because he started with magnetic domains completely randomized, he whacks it on something, you're going to have the little domains do a little jiggling. And so there's a slight chance that they could have aligned a slight amount and made a really, really weak magnet. Of course, it never would have been strong enough to pick up anything. And then there's a second problem. What are keys made out of? What color are all but 1 or 2 of my keys? They're kind of yellowish because they're made out of brass. Why brass? Well, one of the reasons for brass is because it's non-magnetic. You're never going to pick up a non-magnetic key with a magnet no matter how strong the magnet is. Because not all materials are ferromagnetic. And so, that would, MacGyver used to always say, all of these things are real physics. Well, in theory, kind of, yeah. You are never going to actually make a bomb from a pine cone. It's not the right amount of chemicals. Yeah. Okay, so know about the different types of magnetisms. Obviously, the one we spent the most time with was the ferromagnetism. With magnetic charges, there are 2 types, north and south, and we have opposites attract, likes repel. So if I have a magnet, I didn't write here anything about magnetic fields, and I really should have, because magnetic fields are obviously of vital importance. The magnetic fields go out of north and into south. And what happens to the magnetic field when I go into the magnet? They continue through because the magnetic field lines always form loops. They always form loops because, as far as we know, there is no such thing as a magnetic monopole. You can never find just a north magnetic charge by itself. It's always a north with a south. So the net magnetic charge is always 0. Magnetic field lines are always continuous. They never have a beginning or an end. If I put a little bar magnet like a compass out here, what's that compass going to do? It's going to rotate so that in the end, it's aligned so the magnetic field comes out of the north and goes into the south. So there's going to be a torque to rotate it so the magnetic field lines do what they're supposed to do. So make sure you understand just that basic magnetism information. Then we have Amperes Law. Now, I was able to take things from different chapters and different organizations and reorganize them in review because once you have all of the information, you can regroup it and it makes more sense. Amperes Law, Amperes Law says that a moving current is going to create a magnetic field, and I can calculate that magnetic field based on how much current is passing through a surface. So make sure you understand Ampere's law. I can use that right-hand rule to say, okay, if the current is going this direction, wrap my fingers in my right hand around the wire, and if I put my fingertips between the wire and where I want to know the magnetic field, the direction my fingertips are pointing will tell me the direction of the magnetic field at that point. So since Abby's following along here, if I want to find the magnetic field due to a wire that's got the current going down at Abigail's position, I'll first take my right hand and put my thumb down, then orient my fingers so they're between me and Abigail, and then my fingers are pointing that direction. So if I had current going down here at Abby, it would make a magnetic field going that direction. Make sure that you can do that. And then Ampere's law also tells us for a wire, the magnetic field is going to be, you'll have the equation given, mu sub 0, the permeability of free space, multiplied by the current divided by 2 pi times the distance from the wire carrying the current to where I'm finding the magnetic field. That's the distance perpendicular to the wire. So if the wire is like this, it'd be a distance going like that, right? If the wire's like this is like that. So R is not technically radius here. It's the distance, perpendicular distance from the wire to where you find the magnetic field. Okay, so we have Ampere's law there. You should be able to use Ampere's law to find, you should be able to derive the equation for the magnetic field due to a wire with Ampere's law, although you're not going to be given doing that on the test. Right? Just because you should be able to do it doesn't mean I'm going to ask that question. And that's what I'm telling you, I'm not going to ask. Then magnetic force. We have the magnetic force. First of all, there is a force between two charges, two magnetic charges. But we never learned how to calculate the magnetic force between two magnetic charges. In this class, we did not use the force between two magnets. Just didn't do it. We talked about there being a torque to make them align. That was the end of that. Everything that we did had to do with a moving charge, either electrons moving, protons moving, or just simplifying it to a current. That's what we calculated the force for. So you need to make sure you have those equations in a usable fashion in your head. So force between moving charge and magnetic field. Notice the vector signs are vital for this equation. If you don't have the vector signs, that's Q times V times B, which has a completely different meaning. If you have the vector signs, it's Q V cross B. V cross B has a direction and implies that the magnitude of the force is equal to Q VB sine of the angle between the velocity and the magnetic field. So those vector signs are really important to the meaning of that equation. And then you have the right-hand rule. And yes, it's been pointed out that our textbook has an unpleasant version of the right-hand rule. I say unpleasant because it's not the standard. It will still get you to the right answer, but it's not the standard one that you have in most textbooks. And so I've been teaching the standard one to make sure that you can go to any source and you should be able to use it. You're going to have to know the right-hand rule, which is your index finger goes in the direction of the first item in the cross product. Your middle finger goes in the direction of the second item in your cross product. And your middle finger can vary anywhere from parallel with the first finger to anti-parallel with it, going in the direction of the palm. You can't hyperextend the middle finger and put it behind your index finger. And then your thumb points the direction of the answer. So whether it's force equal to Q V cross B or if it's torque is equal to R cross F, it's the same rule, the same right-hand rule for determining the direction. So make sure that you can do things with that. You can calculate the magnitude of the force for a charge moving in the presence of a magnetic field. You can calculate the direction of the force for a charge moving in the presence of the magnetic field. Do also remember with the right-hand rule, your thumb must be perpendicular to both your middle finger and your index finger. You don't put your thumb like this, right? That would be a problem. It's got to be perpendicular to both of these. And cross product is, by definition, multiplying the perpendicular parts. That's why we use a cross. It has perpendicular lines. Then we had the force for a current carrying wire, which I have been very correct with this semester. IL cross B, an obscurity there that we define a vector for the length of the wire instead of for the current. And so it's again a cross product, so you use the same right-hand rule for the directions. And if you were to do the magnitude, it would be the magnitude of the force is equal to ILB times sine of the angle between the length of the wire and the magnetic field direction. So make sure you can use those. You can find the force acting on either a wire or a charge that has, well, moving charge or current in wire with current. Once you have those two plus Amperes Law, then you can find the force between two wires. Now let's do something really simple. Let's say I have 3 wires. I actually wanted to go right here. 3 wires. I have wire A that's carrying current this way. Wire B that's carrying current that way. And wire C that's carrying current that way. Now these are all in the same plane. They're all in the plane of the screen here. Nothing's going in or out. 2 of these wires have no force between them. Which ones have no force between them? A and C. Why do A and C have no force between them? Is what? They're perpendicular to each other. So the magnetic field that's created by, let's say, C is going to be, so C's magnetic field is going to be going, now that is supposed to be in and out of the screen. Let's do it the way we're supposed to. So there's the magnetic field that's produced by current C. And then if we do the current crossed with the magnetic field, on one side, we have current like this, magnetic field like that, and it's coming out. The other side is going in. The net force is 0. Now, there is a torque. Try to make it rotate. But there's no net force. And if we separated them, we usually would say at a distance. So if we have ones like this and then some distance away, there's one like this. Then we'd say, but the direction of the magnetic field out here is perpendicular to the wire. So no force when they're perpendicular. When they're parallel, there's a force. And you should be able to determine right away that this is attractive and this is repulsive. So let me ask a student. I will go to Erika. Let's consider current A here. What direction is the magnetic field at wire B due to current A? Is the magnetic field caused by current A at wire B? So is it going up, down, left, right, in, or out?
I'm thinking like north and south, but no.
Okay, let's go through the process. You didn't get the right answer. That's okay. We're not on the test yet. So the rule is you take your right hand, put your thumb into the direction of the current in wire A. So my thumb is up. And then I wrap my fingers, and I want my fingers to be on the side between wire A and B. So I have my hand like this, and the fingers are pointing into the screen on that side. So that means that the magnetic field at wire B due to the current in wire A is in so there's the magnetic field due to the current in wire A. Does that work? Okay, now going to Amanda. Given that magnetic field at wire B and the current in wire B going the direction of the arrow shown, what direction is the force on that wire? Now, I gave you the answer, but I want you to explain it.
Like using the right hand.
Yes.
So looking at current B, it's still going up to.
Now that you're looking at the rule to determine magnetic field direction. Now we want to look at the one for force. We have more than one, like Arlene was saying. That's it's rule 2 for the right-hand rule, right? Sometimes I do enumerate them, but they're not actually rule 1, 2, 3. So I was like, I don't know. There's not an actual list. But this is the one for the cross product. So the equation here, and I know you may have the answer ready, but I want to make sure everybody's with us. IL cross B. So you want to use that one to find the force created on wire B due to magnetic field in A.
I'm mixing them up.
Well, it's a cross product. What's the rule we use with the cross product? This one. So with that one, we're going to have, what direction should I make my index finger point? Not, yes, up. Yes, up. The direction of the first item in the cross product, which was L. L being parallel to the current. The current not having a direction, right? That's the obscurity there. So my index finger is pointing up, and then I need to orient my hand, so what direction should my middle finger point?
Towards this way.
The direction of which item in the equation? B. So what direction is B at this wire? I have a circle with an X in it, which means it's going away from you. So I need my middle finger to be going away from you. And then my thumb points to the left toward the first wire. So that's how you show that it's attractive. So like if this was on the test, and if it was one of the last 5, you would need to explain how you applied the right-hand rule to get that it's attractive. Right? If it was one of the first 15, you would just have to say attractive. Well, the downside on that is you can just memorize that it's attractive if they're parallel, and you don't have to really learn it. And so we then would calculate the magnitude of that force is equal to IB times length B times magnetic field due to A, which is mu naught IA over 2 pi times the separation. And so that's the equation for the force between the wires. But you had to use the right-hand rule to determine if they're parallel, it's attractive. And if they're anti-parallel, it's going to be repulsive because you change the direction of your index finger from up to down, and all the other finger, the middle finger has to stay the same direction, so the thumb flips. All right. Then we had electric motors. Electric motors, we did our derivation. If you're going to have anything that has to do with a derivation for electric motors, it's going to be a square coil because that makes calculation easier. Right? Square coil, so this side is a straight wire, this side's a straight wire, and so on. And we saw that the net force on the square coil was 0. One force up, one force down, adding up to 0. But the torque was not 0 because torque is R cross F. With torque being R cross F, the R is the perpendicular distance from the axis of rotation to where the force acts. And the R's were in opposite directions, so the torques were in the same direction, creating a total torque. So you should be able to go through that to explain the direction it will rotate, calculate the torque in a certain angle. The torque max was equal to INBA. I, the amount of current flowing through the coil, N being the number of loops in the coil, B being the magnetic field in the vicinity, in the region of the coil, and A being the area of the coil. And remember, it depended on the orientation if it's going to be max or not. Otherwise, we had like torque is equal to NBA sine of the angle between the area and the magnetic field. Pretty sure that was it. It'll be on the equation sheet. You do need to be able to determine, hey, is this maximum torque or is this minimum torque? For sure. Wow. I am so not going to get to my lecture today. I've used up half the class period reviewing the first chapter. The second chapter, Faraday's Law of Induction. Faraday's Law of Induction is the law that says a changing magnetic flux produces an EMF or a current. So the way we learned it was EMF is equal to minus, and I'll put the N outside, change in magnetic flux over change in time. So you have to be able to calculate that magnetic flux again. We had electric flux for the last test. Now we have the magnetic flux. Flux is B dot A. What does the dot product mean? Parallel. Multiplying the parallel parts of the vectors. If we didn't have the vector signs, it would just be multiplication with the dot, but with the vector signs, it's the parallel parts. So that's equal to B times A times cosine of the angle between the magnetic field and the area. Now, you might have noticed up here I had the torque had sine of theta. Here I had cosine theta. The reason for the difference is you have the change in flux divided by change in time. If the magnetic field and area are constant, it's just the angle that's changing. The rate of change of cosine theta is minus sine theta. So that's why it changed from cosine to sine. So you have to be able to calculate that flux. And you can see that your flux will change if the magnetic field changes, if the area changes, or if the angle changes. Any one of those three things will cause a change in flux and thus induce an EMF. And we can use Ohm's law to relate the EMF to the current. That is, the current is equal to the EMF over R. So if you have a circuit with some known resistance and a changing magnetic flux, you can calculate what the current induced is going to be, which is actually the way we usually use this. What did I say was the important, and the textbook agreed with me on this, what I say was the importance of that minus sign? To remind us to look at Lenz's law. Lenz's law says that the induced current will flow in the direction to create a magnetic field that opposes the changing flux. So if your flux is getting stronger, then the induced current is going to weaken the flux, make a magnetic field that's opposing the magnetic field that's already acting. If the magnetic flux is getting weaker, it's going to try to create a magnetic field the same direction as was already there. So you have to look at Lenz's law. It's not just what direction is the magnetic field, it's what is the flux increasing or decreasing. That's going to tell you what direction the current flows. This brought up a slew of very related things. These are all basically applications of Faraday's law. We had eddy currents. You remember my little demonstration with this, with the ring tosser. Those were examples of eddy currents being created because of a changing magnetic flux. In this case, the magnets very slowly drop through it. And this is made out of brass, so no magnetism between them. Magnets slowly drop through because they're creating eddy currents that, by Lenz's law, are creating magnetic fields that are opposing the motion of the magnet, opposing the change in flux. And so it makes a force that's opposing the gravitational force, slowing its descent. So eddy currents were an example of applying Faraday's law of induction and Lenz's law. The Hall effect. The Hall effect is the effect that if I have a current moving through a region with a magnetic field, that there's going to be force on that charge that makes the charge deviate, so it creates an electric field across the charge carrier. So typically you use something like a silicon wafer. You have current going this way. If you have a magnetic field that's in this direction, then current is perpendicular to magnetic field, and it will create a force that's up or down, depending on the direction of magnetic field current, and that will create an electric field going from top to bottom here. And so by measuring the electric field difference or electric field between here, I can determine what the strength of the magnetic field was that's going this direction. If I rotate my probe, now I'll be testing what direction with the strength of the magnetic field in this direction. So the Hall probe allows you to find a component of the magnetic field. You use 3 different orientations for that Hall probe. You can determine the total magnetic field vector in any place by looking at the electric field. And so make sure you understand the aspects of what's going on in that Hall probe, the relationship between the electric field and the magnetic field when I have the charge flowing through. Then electric generators. Electric generators, what's the difference in an electric generator and an electric motor? It's basically just the function. A non-optimized electric generator is also a non-optimized electric motor. The difference is, an electric generator, you're putting work in, you're cranking it, and then you have a wire moving in the magnetic field, so you have a changing magnetic flux inducing a voltage. An electric motor, you're putting current through the coils, and then you have that current is creating a magnetic moment for the coil that then creates a torque to rotate the coil. So the same exact device can be an electric motor or an electric generator. Now, if you optimize them, you make it so it's a better generator, it's probably going to be a worse motor and vice versa. So make sure you understand how the electric generator works. Once again, think about the split commutator idea that we had with the electric motor. Electric motor was in the preceding chapter 22. It's like, that's covered on this test, right? Yes. The split commutator is really important to make a DC electric motor, or you can use it to make a DC electric generator. Then we had mutual inductance transformers. Transformers, you have 2 separate coils. The symbol for a transformer is this. That's the symbol for it. If you put something like an iron core in there, why would you use an iron core to connect the 2 loops? Okay, it's not a current, but I think you're in the right area. That iron core is going to greatly increase the strength of the magnetic field. And by greatly increasing the strength of the magnetic field, you're able to make the coupling between the 2 coils better. As you have less stray electric field, you have less loss. And so if you put an iron core in there, they usually show something like that in between to show there's the core coupling the 2, so that you have the magnetic field created by one coil, it goes through the other one. And then you just have the changing flux in the second coil is going to induce a voltage. So if you put some current in the first one, that's going to create a magnetic field. That changing magnetic field is going to create then a voltage difference in the second one. Now here I have it written current to voltage because that's the way it works best in my head. But it turns out the relationship for a transformer, if it's ideal, is very simple. The voltage 1 over voltage 2 is equal to N1 over N2 is equal to current 2 over current 1. So power 1 equals V1 I1 equals V2 I2 equals power 2. So you have the transformer isn't creating power. It's ideally not losing power. Notice I keep saying ideally. In reality, you're always going to lose a little bit in the transformer. Nothing's perfect. But in the ideal case, you're not losing power. You're just transforming it to a higher or lower voltage. So I was talking with Mr. Hardy last week, and he got a transformer that produces an output voltage of 600,000 volts. Note to anyone around him, you don't want to plug that into the wall and come anywhere close to touching the wires. Because if you plug that into a 120 volt outlet and you get 600,000 volts, it's going to be potentially fatal, right? So you need to be careful. We talked about safety. That was on the last test. You're not going to have more questions about safety in this one. But just pointing it out. Got to be careful with that. So if you calculate the turn ratio in that thing, if it goes from 120 volts to 600,000 volts, 120 times 5,000 is 600,000. So that means you have a ratio of turns from one side of that transformer to the other of 5,000. So if one side has 100 turns, the other one has to have 50 million. 50 million, did I do that right? Yeah. So there's a lot of turns. You had a question, Erika?
Yeah. So I remember when we were doing electric you were talking about how voltage and power, how they were connected. And I think it was that the bigger the voltage, the smaller the power.
Well, I was talking about the transmission lines for electric transmission lines. And in your electric transmission lines, you have a certain power you want delivered. I'll get you now. You have a certain power that you want delivered. And so that means you have a certain voltage times current. And the power that's going to be lost in that transmission line using Ohm's law and Powers VI is going to be the current of the wire itself, the resistance of the wire itself times the current going through it squared. So if you can lower the current through the wire, you're going to have less power lost in the wire. And so using a transformer, you can raise the voltage to a really high voltage, thus lowering the current to a really low current and making the power lost in the wire very low. And so the purpose of the transformers and having really high voltages on our transmission lines is so that we have less power lost in the transmission line. And I think you had a homework problem where you had to calculate that. Is that what you were wanting to know about?
Yeah, I just wanted to make sure so no one studied it wrong and be like, oh, I guess it's wrong.
Okay, Noah, what was your question?
Is it 2/1 for the current?
Yes, it's reversed. It's reversed so the power equation is the same, right? Because V times I is equal, V1 I1 is equal to V2 I2.
Okay.
This times this equals this times this. So yes, it is correct. Okay, so that's a transformer or a mutual inductor. Mutual because it's between two coils. A self-inductor is where you have one coil. If you have current going through the coil, it creates a magnetic field. If that current is changing, the magnetic field changes. That changing magnetic field then is going to induce a voltage. Sometimes if it's like an electric motor, this occurs, and we call it a reverse or back EMF. The faster the motor is going, the bigger your reverse EMF, the bigger the voltage back it is. So an electric motor is always going to be limited by that back EMF. The faster it goes, the higher the back EMF. You're going to have to crank the voltage higher and higher because your voltage in is going to have to be higher than the back EMF or you've reached maximum speed. So once again, a motor is a generator. If the voltage produced by the generator is equal to the voltage that you're putting in, well, it's not going to go any faster. So a self-inductor is the same idea. It creates a back EMF. And so we had the voltage that's produced in the inductor is the inductance times the rate at which the current is changing. Notice for both a transformer and an inductor, they're only useful for us if we have a changing magnetic field, which means if we have a changing current. So if I put a transformer and I connect it to my battery, what do I get every time? For the output, if I put a 12-volt battery on Edwards' 5,000 to 1 turn ratio transformer, what am I going to get out? Get what? The battery is a 12-volt battery. It's DC. So I'm just going to get 0 out because I have to have a changing current for a transformer to do anything. A constant current does nothing. Only for the instant when I connect it will I get something that's not 0. So transformers, inductors, they're only fundamentally useful to us if we have a changing current. So we had 2 situations with changing current: a transient circuit, a circuit where you're changing from one state to another state, or an AC circuit where you have a constantly changing current. Those are the only 2 situations where an inductor is really analyzed. Otherwise, it's just a piece of wire. So make sure, once again, you review the transient circuit analysis, the equations that relate current and time for an inductor. Remember, because the inductor is storing energy in the form of a magnetic field, and that magnetic field is proportional to the current going through it, then the current can't jump discontinuously because the energy that's stored can't just jump. The energy has to be transferred out, which takes time. So current has to be continuous through the inductor. So when you're working with an inductor problem in a transient circuit, you calculate the current going through the inductor just before you flip the switch, and that's going to be the current right after you flip the switch. Can't jump. It will start changing, but it can't jump. The current after a very long amount of time is easy to calculate because after a very long amount of time, you should have reached equilibrium, which in a circuit case means that the current is constant. If current is constant, what's the voltage drop across the inductor? Always 0, because you have to have a changing current to have an induced voltage. So you can make the calculations really quickly about what's going on with the inductor if you find the current just before you flip the switch and the current's going to have after a very long amount of time. And then you just have your equation, the same one as we had for the capacitor. In most cases, you're going to have I infinity is 0 if you're not connected to the battery. If you're connected to the battery, it's, well, you use Ohm's law to find it. Tau, of course, you need to calculate. Tau is equal to L over R for an inductor resistor transient circuit. And those equations are, of course, given in the equation sheet. But being able to use them is just as important as being able to read them. So you should be able to do the transient circuit for LR, just like for the last test, you're able to do the transient circuit for, I said LR, yeah, that was right, for RC. And then we have RLC circuits. Make sure for the RLC circuits you can calculate from peak voltage to RMS voltage. Make sure you can calculate the reactance for an inductor and a capacitor. Make sure you can calculate the total impedance for a circuit, that you can do the phasor diagrams like we did in lab, so that you can solve for the current through an RLC circuit if you know the voltage and you know what the RL and C are. So make sure you can do that. Our circuits will be limited to only the circuit like we had in lab. It's the only kind of AC circuit you're going to see. So it's pretty limited in application there. And the last chapter, which was only spoken about in class on Wednesday of last week, chapter 24, the transition to electromagnetic waves and light. James Clerk Maxwell, deduced that after a lot of work, he could say all of electromagnetism is just these 4 laws. Gauss's law for electric fields, covered in the first exam. Gauss's law for magnetic fields, only tangentially mentioned because the magnetic charge is always 0. And so what that law says is the magnetic flux on any closed surface is 0. It's not useful for any usage that you and I have. It is useful for describing electromagnetism in general. Then the next one, Faraday's law of induction that we've just been talking about. Amperes Law that we talked about for chapter 22, with Maxwell's modification that a changing electric field is equivalent to creating a current. So the changing electric field will create a magnetic flux, or magnetic field. just like a current creates a magnetic field. And and you'll have the equation, you won't have to have it memorized, but you should understand, hey, if I have this changing magnetic field, that's the same as, this current, should be able to do that. Putting those together, then Clerk Maxwell was able to find a wave equation. An equation that says, hey, I can make a wave of from electromagnetic fields. Can't be electric field only. Can't be magnetic field only. Have to have both. But you can make an electromagnetic wave. The speed that was given by his equation was the same as the speed of light, so he concluded, if it quacks like a duck, it must be a duck. Could not be a voice synthesizer. Well, Heinrich Hertz actually did experiments that show that, yes, light is an electromagnetic wave. So now we understand they are. We talked a little bit about the antennae, how you have a magnetic flex antenna, one that has a loop, and if you have a changing magnetic flux through that loop, you'll have a current induced. Or we have the electric dipole antenna that is going to be measuring if you have a changing electric field, it's going to induce a current. So 2 different types of antennae. Electromagnetic waves, you must have mutually perpendicular electric field, magnetic field, and velocity. And the relationship between the velocity, the electric field, and the magnetic field, both at any point and at the peaks, is going to be the magnitude of velocity is the magnitude of the electric field divided by the magnitude of the magnetic field. So we usually only talk about the electric field for an electromagnetic wave, because if you know the electric field, you can instantly calculate the magnetic field from this equation. You have to have both. You can't have only the electric field without the magnetic field. It's always going to be present for the electromagnetic wave. And the final thing that I don't have here is the spectrum, the electromagnetic spectrum. Let me actually go back to the last lecture, the last slide there. I think it was the last slide. The last one, at least, that we talked about. Here's the spectrum. You should have some understanding about this spectrum. You can see marks from last time. That you have the long radio waves, long wavelength, low frequency because of the relationship between frequency and wavelength. Then you have radio waves, and that's where I had to stop when I was talking about the spectrum. So just finishing out. Microwave, micro means short. Microwaves are shorter than these long radio waves. They're longer than everything else, though. So they're on the long side of our spectrum, the microwaves. You go from microwave to infrared, visible. Infrared, infra means below. So infrared is on the side with frequencies lower than red light. Then you go through the visible spectrum, which is magnified here so you can see going from red to violet. And then you have ultraviolet, above violet, higher frequencies than violet. And then above ultraviolet, you have X-rays and gamma rays. The distinction between ultraviolet X-ray and gamma ray is source. Gamma rays come from the nucleus of atoms. X-rays come from core. I'm not going to use the word core. I'm just going to use closely bound electrons, closely bound to the nucleus. So like in the N equals 1, 2, 3 shell. So if you have something like, lead, well, a common material for X-rays is copper. Copper has N equals 4 for the highest electrons. And your X-rays are generally produced by electrons falling down to N equals 2 or N equals 1. And then UV is just any source. So the term X-ray actually, it refers to the source of the ultraviolet light. The term X-ray refers to the source. So you should have this spectrum in your head. The order for radio waves to microwaves to infrared to visible to ultraviolet, and then X-ray and gamma being those separate sections. Yes?
Do you also want us to know the colors?
For this test, no, you don't need to know what the colors are. Just know visible light is there. Okay, any questions about the exam? No.
So the spectrum and stuff is on the test, but not like the stuff that we went over in the reading quiz today, like refraction and stuff.
Right. The stuff for the reading quiz today is the stuff that I would have started right this instant if it wasn't time for class to end. Okay, so I will not have homework that's due on Wednesday. There is homework that's due today from, it's been due for 4 days. Is that right? Or it's been there for 4 days. There's nothing there? Well, I'm not going to add it now then. I will then put homework for Wednesday, the homework that I thought I had set up for today, because I thought I'd set up homework for today. But the goal is I did not want to have homework that was going to impede you from studying for the exam.